Welcome everybody to today's central exercise class in Mathematics 2. As usual, we'll be happy to take any questions you might have. Please ask your questions on our chat channel. The channel is available at chat.tum.de. And please use this channel here, MA9714-CE, to ask your questions. The chat will be hosted by Alind Karlsson as usual. So let's start right away. We'll be discussing sheet number 4 today. We have two central exercise problems on sheet number 4. The first one deals with visualization of a function, basically, and also with the main topics of last week's videos, which were partial derivatives, gradient, and Hessian. And the second one also deals with that topic, plus with the more general idea of differentiation and the total differential. So let's start with 4.1. So in this problem, we have a function that's defined on R2. So R2 is the coordinate space. We have two input coordinates, and it maps to R. So the function value is always just a real number. And the function is defined as f of x1, x2 is x1 squared minus x2 squared. So pretty basic multivariate polynomial. The question is, sketch the level sets of f and the graphs of the restrictions of f to the coordinate axis. And then also we have to determine the gradient and the Hessian of that function f. Okay, so let's maybe start with the restrictions of f to the coordinate axis to get an idea of how f looks like if you view it based on one coordinate axis. So let's see if we restrict f to the x1 axis first. So that means we're moving in x1 direction and we're fixing the value of x2. Okay, basically, let's try 0 first. If we fix the value of x2 to 0, then we get another function. Let's call that g1 of some parameter lambda. And we'll define that as f along the line that passes through 0. And the direction of that line is the x1 axis. So we have lambda times the vector 1, 0. And this here, that is the line with direction 1, 0. And it passes through the origin, through that point 0, 0 here. So basically, we're fixing x2 at 0, and we're moving just along the x1 axis precisely. And if we do that, well, we can just use the definition of the function f here. So the x1 part is then 0 plus lambda times 1. So that's lambda. And the x2 part is 0 plus lambda times 0. So that's 0. So we have is f of lambda and 0. And if we just substitute that here into this definition, we get x1 squared, that's lambda squared, minus x2 squared, and x2 is 0, so 0 squared. And of course, that's just lambda squared. So that means if we consider the function along the x1 axis, it basically looks like this here. Let's see. So what we get is a function that looks somewhat like this. That's our function g1 of lambda. And here's the x1 axis. And here's g of lambda. Okay, so locally, that along that line, the function looks like a parabola that opens above. Of course, if we fix x2 at a different level, let's quickly consider that option as well. Different x2 level. Then what we get is g1 of lambda, again, call that g1 of lambda. A different x2 level basically means that that we evaluate f along the line given by the same direction. So we again have this lambda 1, 0. For the x1 axis, we move along the whole x1 axis, so it doesn't really matter where you start on that axis. So we can just keep that point here at 0. And to fix x2 at a different level, what we do is we just change that point here to some fixed x2 star. So we consider that some fixed value. And what we get is basically what we got before. So we have f of lambda and now of x2 star, where only the lambda varies. And that means we get lambda squared minus x2 squared. So depending on the value of x2, that parabola here might not be this. That corresponds to x2 star equals 0. Sorry, I forgot the squared here. But we get a parabola that is slightly shifted downwards, like this, or this, or this, right? So basically, it always looks like this parabola, but it shifts according to the x2 value that we fix. And of course, if we do the same thing along the x2 axis, so basically now we restrict f to x2 axis, meaning we fix the value of x1, 0 in the easiest case. And we just vary the value of the x2 input. Then again, we get a function, let's call it g2 of lambda. That will be f of 0, 0 plus lambda times 0, 1. So we only move along the x2 axis. That means the x1 input is 0. The x2 input is lambda. So we get 0 squared minus lambda squared, and that's minus lambda squared. And now, of course, if we sketch that graph here, we basically get something that looks like the one before, but the parabola is now flipped. So that's our G2. Now here's the x2 axis, and here's our G2 value. Okay, so if we're looking at that graph for a fixed x1 value and only vary the x2 axis, then it looks like a parabola that opens below. Okay, so situation is kind of flipped. And again, if we fix the x1 value to something other than 0, what will happen is we get some positive value here, here, and consequently that's not going to be 0 squared, but some x1 star squared. So again, this parabola shifts up or down as we vary along the x1 axis. Okay, so that's what happens to that graph. And you can probably guess how that looks like. In case you can't guess, I try to plot that for you. Let's see if I can share that window. Just a second. So I hope you can see that now. That should be the plot, the surface plot first of that function. Here's the x1 axis. You can see my mouse pointer here. And you can see, let me rotate that a little. So if we look at, we look at that, basically only along the x1 axis, then you can see this looks like parabolas shifting down. And if we turn that to look at it only along the x2 axis, and you can see that again looks like parabolas. Now we're shifting upwards. And the parabolas are now bent in this way, right? Opening below instead of above. And the whole thing, the whole surface kind of looks like a saddle. And that's also what this is called. It's called a saddle surface, right? So it bends upward in this direction and downward in the others, where the legs go on the saddle. Now, if we want to sketch the level sets of this, what we do is we cut through this graph here. So let me quickly insert that here. A static picture of that here. Let me change the screen so I can see that. Just a second. So here's that plot again. And now, again, for the level sets, we need to cut through that at constant levels of the x3 axis. So we're taking constant levels along this axis here. Basically, for example, we're fixing this plane here, and we're cutting through the graph along this plane. What we get is a cut through this set and also a cut through the level here. It's harder to see, but you should be able to see if we cut through this here, we get a curve, looks something like this, yeah, along this curve here. So basically, that's the kind of plots that we'll get. And of course, as we move downwards, we'll also get cuts here through that surface types. Let me again switch to the interactive plots so I can show you that from different angles. So here is basically the contour plot, the level sets, but with the corresponding actual heights. So if you look at the graph like this here, basically you can see these lines here on both sides. And the blue lines down there again on both sides. And let me rotate that a little so I can actually see both, like here, one in the front, one in the back. And you can also see that great cross here in the middle. That's basically where the saddle point is. And now the contour plot basically is looking at that from straight above so that it all becomes flat and is embedded in the coordinate plane. So something like that here. Yeah, that roughly should be the contour plot. And that's exactly what it looks like. Again, let me change the screen. So here we go. We should now be able to see my iPad screen once again. So that's how the level set plot looks like, contour plot. And you can see those curves here. And on the other side, so that's symmetric. You can see those curves here. That's from the other parabolas. Those are going down, right? These and these. You can see that cross in the middle at level 0, and that's exactly where that saddle point is. It corresponds to this point here in the middle. Okay, so that's how the level sets look like. Questions up to this point before we determine the gradient in Hessian?
Yes, there are a few. So in the first sketch you have, is the x-axis x1 or x2? Is it written?
So let me draw that here. So this here, this axis, that is the x1 axis. This is the x2 axis. And that axis going up, this one, that would be the x3 axis. So that's where we have the function values.
I think the first figure means the one where you restricted to x2 being constant. So that one, yes.
This one here. Oh yeah. Okay. So oh yeah, that is of course wrong.
Maybe not an x2. That explains the question.
Supposed to be this one. Yeah. Thanks.
And then there's a question: how many level sets are they supposed to draw?
Hard question, as many as necessary to kind of grasp the idea. I mean, in that case, it's pretty easy, right? You have levels of this type here and symmetrically this type, and you have levels of this type and of this type. So I draw maybe 2 of each. And then the one level that is different is at cross. So that should also be there probably, right? Identifying the saddle point here in the middle. So basically the question is, where do they change? Where do these level sets change their behavior qualitatively? And so for each different class of level sets, so to speak, there should be 1 or 2 representatives.
And then the last one is, are they supposed to also sketch such a graph in the exam? But I'm not certain if that means the saddle or the level sets.
The level sets, I'd say yes, maybe. For the surfaces, probably not. We'd have a hard time correcting that. What you should be able to do is, of course, you should be able to find the correct surface plot for a given function or something like that, yeah, as on the exercise sheet. For the level sets, I would say you should be able to draw these at least roughly, but not for the surface plots.
Okay, that was it.
Okay. Then let's go on with the easier part of that problem, which is gradient and Hessian. So let's write down the function once again. It was f of x1, x2 equals x1 squared minus x2 squared. The gradient simply consists of the partial derivatives. So what we need to do is we need to determine df dx1. So the partial derivative with respect to x1 of f. And basically what that means is we treat x1 as the variable, we differentiate for that, and we treat everything else as constant. So x2 is treated as a constant with respect to this x1 differentiation. And that means we have this function x1 squared, we differentiate that with respect to x1. So we get 2x1, and the x2 is treated as a constant. So differentiating a constant will yield 0. So that means this first partial derivative is just 2x1. For the second partial derivative, same idea, but now you treat x2 as the variable. You differentiate for that, and all the others, x1 in this case, are treated as constants. So this here becomes 0 when you differentiate it, and this here becomes 2x2, and we still have a minus here in front. So we get minus 2x2. So those first partial derivatives that give you the gradient. So basically that's an abbreviation of the vector of all partial derivatives. So we have df dx1 and df dx2. And in that case, that is 2x1 and minus 2x2. So that's the gradient here. And for the Hessian, basically, we just take the derivatives of the functions of the gradient once again. So this is the first function of the gradient. This is the second one. And we differentiate each of those with respect to x1 and x2. And that will yield a matrix. So the first line of the matrix corresponds to that first function. The second line corresponds to that second function. And that means for the Hessian, what we get is, so this function, if we differentiate that with respect to x1, once again, we get 2. If we differentiate that with respect to x2, we get 0 because there's no x2 in there. For that second function, if we differentiate that with respect to x1, we get 0. And if we differentiate for x2, we get minus 2. So that's the Hessian, right? On a more abstract level, what we do here is we compute d squared f dx1 squared. So we're differentiating with respect to x1 twice. Then we have d squared f dx2 dx1. So we're differentiating with respect to x1, then x2. Similarly here we differentiate with respect to x2 first, then x1. I forgot the x. And here we differentiate with respect to x2 twice. Right, so that's what's happening here. So basically, again, the first row of the Hessian, that one here, corresponds to the first row of the gradient, and the second row corresponds to the second row of the gradient. So that's the idea, and we'll soon learn how to determine stationary points and how to determine types of local minima and maxima from that information of the gradient and the Hessian. Okay, basically, that's the first problem. Questions?
No more questions.
Good.
As far as I see.
C42? That's going to be a little more abstract. We have a function R2 to R defined as f of x1, x2. That definition has two different cases. The function is defined as x1 squared times x2 divided by x1 squared plus x2 squared. And obviously that expression is not defined at the origin because the denominator would be 0 then. So this holds for all x that are not equal to the origin. And at the origin, we simply assign a fixed value of 0. So that's true for the origin. Another task here is to consider that function and see what we can learn about the derivatives and the partial derivatives of that function. So first we consider f along lines through the origin. Obviously the origin is the interesting point here, yeah, because that is where that definition here changes to that constant. And we're going to show that f is differentiable. So sorry, we're going to show that along each line through the origin, that f will have a derivative along each line. So the restriction to each line will be differentiable. And that will mean the total differential of f can only be the 0 vector. We'll see how to get to those numbers. But it will turn out that f itself is not actually differentiable at the origin. And we're going to show that too. And we're also going to get to the kind of root cause of that problem. So let's start with A, sorry. In A, we consider lines through the origin. So we start with a line, consider a line through the origin. We give that a direction. Let's say that direction is d1, d2. Like this, two-dimensional vector. And of course, the 0 vector is not a valid direction, so we exclude that one. Through the origin, that is 0, 0. That means the line is given as lambda times d1, d2, lambda in R. That's a line in the coordinate space through the origin. And the question is, what do we know about f along that line? So we evaluate f along that line. And basically that means we have an x1 coordinate lambda d1 and an x2 coordinate lambda d2. So we need to evaluate f of lambda d1, lambda d2. Now we just use the definition of our f. Of course, if lambda is 0, then we have f of 0, 0. Nothing changes then. If lambda is not 0, then as d is not 0, at least one of these coordinates is not 0. So that means we'll only consider the case that lambda is not 0 for now. Just to make notation a little more concise. We'll add the remaining case later on. Okay, in that case, we're in this part of the definition, so we can just substitute lambda d1 for x1 and lambda d2 for x2. And if we do that, we get, let's see, we get lambda d1 squared lambda d2. And we divide that by lambda d1 squared plus lambda d2 squared. And that means what we get is, so we have lambda squared times lambda, that's lambda to the power of 3 in the numerator, times, times d1 squared times d2. And in the denominator, we get lambda squared times d1 squared plus d2 squared. And you can see that's simply lambda times d1 squared d2 divided by d1 squared plus d2 squared. And if you look at that closely, you'll see that this here is exactly the definition of f of d1 and d2. So we can abbreviate that by saying, well, that's the same thing as lambda times f of d1, d2. Right, so basically we evaluate f of the direction vector, and then the real function value will be lambda times that value. Okay, so along the direction, along each direction, we just have that simple linear function. And of course, for the origin, so f of 0 times d1, 0 times d2, well, that's simply going to be f of 0, 0. By definition, that is 0. And of course, that's also 0 times the function value at 0, 0, yeah? So this here holds for any lambda, even for lambda equals 0. And that means, to summarize, we can say along that line, we have f of lambda d1, lambda d2 is simply equal to lambda times f of d1, d2. So that's a nice, short, concise way of writing this. And that will hopefully be helpful for the computations that we have to do. Okay, so that's evaluating f along a line. Now the question is, what about differentiation? So if we consider the directional derivative of f along such a line, can we compute that? Do we know what that is? So now we want to compute directional derivatives. Of f. And we need to fix the direction for that, of course. Let's say that direction is now v, to not be confused with the d for differential. We use v now. And of course, that direction will again be a vector in R2. And again, we need to exclude the 0 vector because that's not a valid direction. Okay, we want to compute the directional derivative. Again, we are interested in the origin, and that corresponds to the directional derivative at 0. So we're computing df dv at the point 0. We know how f behaves along a line, so we can just say, well, this is the limit of lambda to 0. And then we just need to consider that function f restricted to the line in direction v. So that's f of lambda v1, lambda v2, minus f of 0, 0, divided by lambda. That's simply the one-dimensional definition of the one-dimensional derivative. You'll hopefully remember that one. Well, we know how to evaluate f along a line already. We find out that f of lambda times a vector is the same thing as lambda times f of that vector. So we can just replace that by lambda times f of v1, v2. Well, f of 0, 0 is just 0. The number 0, that should be more clear. And we divide that by lambda. Well, and of course, now we can just cancel out the lambda here. So what we get is f of v1, v2. It does not depend on lambda anymore, so no need to take a limit here, right? So that is the value of the limit. So that means the directional derivative of f at 0 is defined, and it simply is equal to f of v1 and v2. Okay, so that means the directional derivative of f at 0 exists for every direction v, and its value is f. Well, let's write that like this: dv f of x of 0, sorry, is f of v1, v2. In particular, of course, we can consider as directions our coordinate axis. We can consider the x1 axis and the x2 axis. And in that case, we get those values here in particular. So d1 f of 0 is simply f of the vector 1, 0. And now again, if we scroll back to the definition of f, that would mean here. So we have a 1 here, a 0 here. That gives us a numerator of 0 and a denominator of 1 plus 0. So obviously that value is equal to 0. And of course, the same thing happens if we consider the x2 axis. Then by what we just found out, this directional derivative, this partial derivative is f of 0, 1. And again, that's 0 if you just substitute those values into the definition of f. Okay, so we found out the partial derivatives are both 0. That means, of course, the gradient of f at the origin is 0, 0. And that means the only possible candidate for a total differential, if f was totally differentiable, would be this vector here, this 0, 0 vector, right? So that means if f is in fact totally differentiable, then df, the total differential at 0, would also have to be this vector. And remember, totally differentiable basically means we can approximate f locally through a linear or an affine linear function, more precisely f of x around 0. I'm doing this around 0 now. So that would be f at 0. plus this total differential, df at 0 transposed times x minus 0, plus some remainder. So basically that captures the part that is not captured by the approximation. So this here is basically a plane in three-dimensional space that contains that point 0 f of 0. And the direction is given basically through this vector here. And this here, that remainder part that captures the behavior of that function that is different from the plane. So the error of the approximation, basically. Right, so this here is the approximation error. And we want the approximation to be good, close to our point 0. And that means the limit of that approximation error here compared to the distance of x from our point 0, from the point where we approximated the function, that limit needs to go to 0. So the error becomes small, faster than we approach the point where we computed the approximation. That is the limit as x goes to 0 in this case. Right? So in general, you don't have 0, you just have an arbitrary point that you chose. Here, everything we talk about is the origin. So that's why there's 0 everywhere. Okay, and as it turns out, the only candidate is this gradient here, 0, 0. So basically the approximation itself would be f of 0 is 0. The 0 vector times something is also 0. So the approximation is a flat plane that's constant at 0. And everything else is then approximation error. So basically the question is that error sufficiently small if we're close to 0? In that case, the function would be totally differentiable. So before we go into that, let's stop for a moment and see if you have any questions.
So I don't have any questions for this problem. I have 2 questions for the last one that came in a bit later.
Maybe let's go on with that problem first.
Yeah, I think that makes sense.
And then talk about those later. Okay, part B. We know already that if f is totally differentiable, so if such an approximation here, like this one, if that approximation exists, and if the error is sufficiently small, meaning this limit is 0, then the only candidate is the flat plane at level 0. So basically what we have to do is we have to see if this limit condition then holds or not. And unsurprisingly, hopefully it will turn out that this is not the case in general. Okay, so again, we already know that if f is totally differentiable, then df of 0 is the gradient at 0, and that gradient is 0, 0. We just computed that. So in that case, we can compute this remainder. So the remainder at x, if you look at this line here, you can see that remainder. The remainder is then given as f of x minus f of 0 minus df 0 transposed x minus, well, just x. So minus 0 is, of course, x. And when we know that this here is the 0 vector, so 0 transposed x is going to be 0. We know that f of 0 is 0 by definition. So that means the remainder is the same as the function value outside of the origin. So we have to verify whether this condition here holds or not. This one here. So we verify that limit of x to 0, r of x divided by the norm of x is 0 or not. Maybe that's not even the case. So we need to look at this limit here, and we have already found out that r of x is actually f of x. So we're looking at that function here. And again, to be able to evaluate that, in a way, we're going to consider a line. And in this case, we're consider the line in direction 1, 1. Yeah, so we've considered the axis already. Basically, we've considered every line already, but we're going to look at this because this will make it easy to get a result here. And you'll see in a minute why. So if we do this, we want to compute the limit along that line first. And that means that line is represented as lambda times 1, 1. The origin corresponds to lambda being 0. So the limit of x to 0 corresponds to the limit of lambda to 0 along that line. And we compute f of lambda times 1, 1. And we divide that by lambda times 1, 1 by x, right? And the norm of that. So that's our remainder here. And that means what we have is f of, well, lambda lambda divided by lambda times the vector 1, 1. That's, and the norm of that. The norm of that is simply the absolute value of lambda. And the norm of this vector 1, 1 is square root of 2. Can compute that right away. And we can also compute f of lambda lambda. That is simply lambda to the power of 3 divided by lambda squared. Oh, sorry, I forgot the limit. Let me rewrite that. So once again, that's the limit as lambda goes to 0. Let's write that denominator here first. And then we have this f of lambda lambda. Again, that's lambda to the power of 3 divided by lambda squared plus lambda squared. So obviously we can cancel out a lambda squared here. And we are getting lambda over absolute value of lambda times 2 square root of 2. And again, I forgot the limit. Sorry about that. And now to compute that, well, we need to get rid of that absolute value of lambda somehow. So let's just consider the limits from above and from below separately to make that easier. So limit as lambda goes to 0 from above of that expression. That will then be the same as, well, in this case, lambda is positive. So the absolute value of lambda is the same as lambda. So that's simply 1 over 2 square root of 2. And we can consider the limit as lambda goes to 0 from below. And again, compute that. Now in that case, lambda is negative. So that means the absolute value of lambda is minus lambda. So we get lambda divided by minus lambda 2 square root of 2. And that's minus 1 over 2 square root of 2. And now obviously those two do not agree. So that means that limit does not even exist. So the limit of that remainder, lambda lambda, over, sorry, over lambda, no, lambda times 1, 1, like this. That was our original limit that we wanted to compute. That does not exist. Right? Much less is the limit going to be 0, as we wanted it to be. It doesn't even exist. So that means the function does not have a total differential at 0. The only possible candidate doesn't do what it's supposed to do. So there is no total differential. Right? So that means f is not totally differentiable at the origin 0, 0. Okay, and that's what we're supposed to find out in part B. Questions about this?
So I still have no questions about this exercise. Probably they need to digest it a little bit before they type out something.
Probably yes.
But do you want the other ones while we wait, or?
Let me finish up with CU.
Right. Yes.
And then we talk about the other ones. So last part on that problem here is part C. Show that the partial derivative df by dx2 is not continuous at 0. So basically that's something that we'll learn soon, sometime this week, I guess, in the videos this week. So a function is totally differentiable if the partial derivatives exist and are continuous. So basically, if a function is continuously partially differentiable, then it will be totally differentiable. This one has partial derivatives, but no total differential. So the partial derivatives need to be non-continuous somewhere. And that's what we're going to verify in part C. Actually, there is a partial derivative that is non-continuous at 0. And this is df by dx2. Basically, we just need to find the right line to see that, or the right curve in general. So let's see. We need to see whether this is continuous or not. So we first need to compute it, of course. At the origin, we know its value already. So we already know that df dx2 at the origin has a value of 0. We've computed that before. Right, see part A, I think that was. And now we need to have a look at that function outside of the origin and then see if that function is continuous at 0. So if the limit as we go towards the point 0 really becomes the function value, which is 0 at that point. Okay, now let's compute df dx2 of x outside of the origin. And that means outside of the origin, we can just resort to the definition here. Outside of the origin, f is defined as x1 squared x2 divided by x1 squared plus x2 squared for x not equal to 0, 0. And that means we can just use that expression to compute our partial derivative with respect to x2. So df dx2 of x1, x2 is, we need to use quotient rule as usual for that. So first we take the derivative of the numerator with respect to x2, that's simply x1 squared. We multiply that with the denominator. That's x1 squared plus x2 squared. And then we do the opposite, meaning we keep the numerator and multiply by the derivative of the denominator. So the numerator is x1 squared x2, and we multiply with the derivative of this denominator with respect to x2, that would be 2x2. And we need to divide that by the denominator squared. So x1 squared plus x2 squared squared. Okay, and if we simplify this a little, we get, let's see, we can do something here. So we have x1 to the power of 4 here. Then we have x1 squared, x2 squared. And I think I made a mistake somewhere. I did. Sorry, this of course needs to be a minus sign here, not a plus sign. We draw this in red so you can see what I changed. There's a minus sign here. Otherwise, there won't be much simplification. Okay, once again, so the x1 squared, that's x1 to the power of 4. That's still true. Then we have x1 squared, x2 squared. And there is a minus x1 squared, x2 squared times 2. So we get minus x1 squared, x2 squared here. And that's it. And we just keep the denominator as it is. Okay, now this is the second partial derivative outside of the origin. So we need to see whether this is a continuous function if the value at the origin is set to 0, as we know it has to be. So the question is, again, can we find a line or some other curve such that along that curve, the value is not going to converge to 0? And well, with some meditation, looking at that function, we can actually see that this is the case. And we're going to restrict the function to the x1 axis now. So we consider the line, the x1 axis, 0, 0, plus lambda times 1, 0, lambda in R. And if we evaluate df dx2 along that axis, that means we evaluate that at lambda and 0. Well, what happens is, now we just put a lambda instead of the x1 and a 0 in place of the x2. Then we get lambda to the power of 4 minus 0 over lambda squared plus 0 squared. So that means we have lambda squared, lambda to the power of 4 over lambda to the power of 4. So that's 1 for all possible values of lambda. So that means along that line, this second partial derivative is constant and the value is 1. So it cannot converge to 0 if we get closer and closer to the origin. Indeed, the limit at 0 will be 1. So that means the limit along that line here, oops, df dx2 of lambda and 0, that limit will be 1, and that is not 0, which would be the function value of that second partial derivative at 0. So that function is not continuous. So df dx2 of x is not continuous at 0. And remember, for non-continuity, it's sufficient to find one line or one curve or one sequence in general, such that the function evaluated at that sequence or along that line is not continuous. It doesn't matter whether it may be continuous along other lines. We need every possible path towards 0. And there's one path where the function is obviously non-continuous. Okay, so this means the second partial derivative is not continuous. And that's why that usual theorem doesn't apply. If all partial derivatives exist, and if they are all continuous, then the function is totally differentiable, and this is not the case here. So the function does not have to be totally differentiable, and indeed it is not, as we've seen before. Okay, so this concludes C42. Any questions about C42 as of yet?
Yes, now I have questions. So going back to the B, where did the 2 squared of 2 factor come from?
Let's see if I can find that place. 2 squared.
Yeah, it's here.
Here?
Yes, I think in the first step you get the square root of 2.
This one here?
Mm-hmm.
So that is the norm of that vector 1, 1. So basically here I have the norm of lambda times 1, 1. And we know that for norms, right? The norm of lambda times a vector is the same as the absolute value of lambda times that norm. So that's the first thing I do. I take that lambda, I move it out with an absolute value, and then I just compute the norm of 1, 1. And that's square root of 1 squared plus 1 squared, square root of 2.
And then the factor 2 comes from evaluating f at lambda lambda. Oops.
This one here?
Yeah.
Yeah, basically that's this lambda squared plus lambda squared that we get from this evaluation. So it's 2 lambda squared. And I'm canceling out the lambda squared. So only 1 remains here. I'm canceling out the lambda squared. So that's 1 plus 1, and that's 2. That's where the 2 comes from.
Mm-hmm. Okay, so, and then there was a question, how do you prove total differentiability? Like, is there a general procedure, or how should they know how to proceed?
So usually the easiest case is if the function has all partial derivatives, and if they are all continuous at the point in question or at all points in question, then you're good. And that's what usually happens. In most cases, this will be the case. So you don't have to do anything more complex then. If that is not true, you'll basically proceed like we did in this problem here. So what you'll do is, you know that if the function is totally differentiable, then the only candidate for this total differential is the gradient at that point. So you first compute the gradient. And then you know the total differential, you know what it would look like if it exists. So basically all you have to do then is prove that this actually works. And proof that this actually works means you compute this remainder of the approximation at the point in question. And then you prove that this limit here is actually 0. And that's usually the hard part.
Okay. And then there was a question, you had this transpose sign appearing in B, and why do you need that?
Basically a matter of definition. So for the total differential, we defined the total differential to be a vector G with exactly that property here, G transpose times. So that's the scalar product of G and that vector X minus 0 or X minus X star in general. And that's why I want that here as well, right? I'm just defining the total differential to be a column vector, and then I need to transpose that to get an actual scalar product here, because of course I want the real value to approximate my function. That's a real valued function, so I need the summands here to be real numbers as well. Otherwise, it just wouldn't work. Of course, you could also define the total differential to be a row vector from the very start, and some people do that. So sometimes you'll see the transpose is missing. The difference here is I'm using column vectors. They might be using row vectors. That's mostly a matter of convention.
But if you mess it up, you won't be able to actually like compute their product.
Right.
So
right. So you always make sure that this product here is going to be a real number, that this is going to be a scalar product, right? Yeah. So whatever convention you use, make sure to be consistent here.
Okay, and then there's one question for C. So someone wonders, why did we reformulate the fraction in C that way?
Which way? Which fraction?
Yeah, I am not 100% sure. you can add some
Basically,
comment to your question.
That's not a reformulation here at this point. Well, this is just simplification, not much magic. So I'm guessing you refer to this one here. And basically, the idea here is to find a line or a path or any sequence such that that function df dx2 along that line does not converge to 0 as we get close to the origin, because we want to show that there is a jump that is not continuous at that point. And we know the function value at 0 is 0. So we're looking for some line where the function value is not 0. And what just turns out that if you set x2 to 0, you get rid of this term here. That makes it easier. And then we're basically left with an x1 to the power of 4, x1 to the power of 4. So just setting this direction to 1, by basically going along that x1 axis means that this cancels out and we'll be left with a constant. That's just the easiest thing I could think of here. And there'll surely be other, maybe more complicated paths that will do the same. Yeah, so that's more or less a deliberate choice.
Okay, there's one question coming from A. Why do we only consider the two particular directional derivatives f10 and f01?
So these two here, well, we did consider every possible direction before, and we found out that actually the directional derivatives exist at 0 for every possible direction, and we even computed their value. So if you know the direction, you can compute the value. So we considered all. And then what we wanted to do is we wanted to find a candidate for the total differential. And again, the only possible candidate is always the gradient. And that's why we computed the gradient here. And for that, we need those two partial differentials. So that's why we just used our results before, specialized the directions to the x1 and the x2 axis to get the partial derivatives.
So now I only see someone typing a question, but I don't have. Okay, so I got at least a clarification of the fraction in C. So he means that f of x1, x2 is equal to for x not 0, 0. Yeah, the first big fraction.
This one here. Well, that's just the definition of our function f. So if you look at that definition here, so outside of 0, f is defined as this fraction here.
Okay, and what happens between this and the next step? So I guess going to this big expression.
Oh, this and this. So what we do here is we take the derivative of this expression with respect to x2. So basically we'll treat x1 as a constant and then compute the derivative with respect to x2 of this term here. And we do that by using quotient rule. So we first compute the derivative of this numerator here with respect to x2. Well, that's constant squared times x2. So that's just constant squared, right? This is left times the denominator. And then we subtract the opposite. So we now take the numerator as it is and multiply by the derivative of the denominator, again with respect to x2. So this is considered a constant that vanishes, and the derivative of that is 2x2. That's the term here. And that will be divided by the denominator squared. It's just the quotient rule of taking one-dimensional derivatives.
Yeah, he's happy now. So
good.
That's the question. So I don't have anything more for the second problem.
Okay, wonderful. So let me mention if maybe you'll need some more time to digest that second problem. And if any more questions pop up, then of course you're welcome to ask at our tutorials. Unfortunately, no tutorials this week. Let me also mention this. So there's a public holiday this Thursday. So if you happen to have any more questions, you'll probably have to postpone that to next week. But we'll be happy to help there. Even if you ask about older sheets, that's fine, of course.
I still have the 2 questions
So-
from the first problem.
Let's talk about the
I
first
just-
problem once again.
So there was
scroll
one
back.
question of what the Hessian would look like if you have more variables.
If you have more variables, you basically get more columns. And of course, also more rows because the gradient also becomes larger, right? So for each variable, you get 1 row in the gradient that corresponds to the rows of the Hessian. So that gets larger. And each column of the Hessian corresponds to 1 variable as well. So the Hessian is always a square matrix and it just grows as the number of variables grows.
And then the last one is, how do we know how many classes of level sets a function has?
Well, basically, you have to have a look at the function and see if you can find out where it changes its behavior. That's I can't give a recipe for that, unfortunately.
Yeah.
Basically, a mixture of experience and meditation.
And practice. So do
In
that.
practice, you'll probably
Differentiation
use some plotting program to see what happens there, to be honest.
Okay.
Which, of course, you can't do in the exam. Or maybe, well, we don't know about that yet. I hope we'll have a definite answer of that as well in a few weeks at most.
Okay, so that's what I see. Hope I didn't miss any questions, but I think that was it.
Okay, wonderful. So as I said, no tutorials this Thursday, unfortunately. Also no lecture Q&A, but of course, tomorrow's Q&A session will still take place. So if you have any questions, you're welcome to register for that Q&A session. I think there's still some free places for that one. Otherwise, I'll see you next Monday. Thanks a lot to Erlind for the moderation. And I guess I'll also see you next Monday.
Yep.
Good. So goodbye and see you then.